In this section, we're going to look at some applications of radian measure in particular. So it's going to be really important that the angles we consider are measured in radians. The formulas that we are going to use only work when we measure the angle in radians. So the first formula, the first application is to find the length of an arc along a circle. So if we have a circle of radius r, if we have this, we call this a central angle, theta, then the measure of this arc, which we're calling s, is given by r times theta, as long as theta is measured in radians. So here, if I want to find the length of this arc, the radius is 3 inches, the angle is pi over 6 radians, and so we start with our formula, s equals r theta, that's 3 inches times pi over 6. Now it's pi over 6 radians, and I mentioned in another video, radians are considered to be dimensionless. And so when we do this multiplication, our units are just going to be inches. The radians don't add any dimension to this. So 3 times pi over 6 is pi over 2 inches. And we could approximate this and get 1.57 inches. Let's do another one. A nautical mile is defined to be the length of arc along a great circle of the Earth for a central angle of 1 minute. And it has been found to be 1,852 meters. We want to know what's the measure of the Earth's radius. So, okay. So a great circle of a sphere in general, and we're kind of considering the Earth to be a perfect sphere for the purposes of this problem. A great circle is like a circle you measure around at the widest point. So just consider that we have a circle around the Earth, that we've drawn this circle around the Earth, and the central angle of 1 minute. So we have to remember that there are 60 minutes to 1 degree. And we need, we know the arc length, right? So just kind of sketching out our approach here. We know that s is r theta, and we're being asked to find the Earth's radius. So if we take this equation and divide both sides by theta, then we know the radius is s over theta. We know what s is. They told us that that arc length is 1,852 meters. And then we need to divide by theta, but we don't know what theta is. We know that it's 1 minute, but we need our angle to be measured in radians. So we're just going to convert this 1 minute to radians. So use a little dimensional analysis. 60 minutes to 1 degree. That would get us to degrees. Now I want to get from degrees to radians, and that equivalence is 180 degrees to pi radians. We could see the units cancel. We're left with radians, and we have pi over 60 times 180 is 10,800. So that's what goes here. We're dividing by this fraction, and so that means we're going to just multiply by the reciprocal. So we have 1,852 meters times 10,800 over pi. We get, let's see, 6,366,707 meters If we like, we could convert that to kilometers, get 6,366.707 kilometers. Now, if you were doing an exercise like this and checking your result, note that the measure they gave us, 1,852 meters, for that arc length has 4 significant digits. So it's pretty likely that they would round the result to 4 significant digits. So that would be 6,367 kilometers. All right, our next application is finding the area of a sector. A sector of a circle. So again, it starts by looking at the circle of radius r, and we have this central angle theta. And then I'm drawing this angle out. You know, I can see the arc length here along the side, but the sector is just sort of that slice of pie there. And we're looking for the area of that sector. And that formula is theta r squared over 2. Again, as long as theta is in radians. Theta must be in radians for this formula to work. So we're going to find the area of a sector with a central angle of 218 degrees and a radius equal to 5.25 inches. So here they've shown it to us. The only thing I really need to worry about, they gave us the angle, they gave us the radius. I just have to get that angle in radians. So I'm going to start with a little conversion. 218 degrees. I know there are 180 degrees in pi radians. We get 3.805 radians. So now I'll use this in the formula. So we have theta r squared over 2. That's 3.805 times 5.25 inches squared divided by 2. Now we're going to get square inches as our units because we are squaring the inches here. We're squaring everything there. So we have 3.805 times 5.25 squared divided by 2. We get 52.4 square inches. All right, let's try it again. Let's do another one. Here they've given us the radius and they've given us the area this time. We just need to find the angle. So we'll start here. There's our formula, theta r squared over 2. We want to solve for theta. So we could just do a little algebra at the outset. I can multiply by 2 and divide by r squared on both sides. And when we do that, we find that theta is equal to 2a divided by r squared. And we're ready to plug in our values. 2 times 75.5 divided by the square of 12.2 we get 1.01 radians. This is in radians. I know it's in radians. In order for these, you know, the other side of the coin about, you know, we say that these formulas only work if theta is in radians. And so the flip side of that coin is that if we're solving for theta, it is automatically in radians. And we need to understand that. All right, one more type of application to look at is angular velocity. So imagine like a wheel spinning, basically. And an angular velocity is the, you know, well, I guess it's exactly what it sounds like. It's how many, like what measure of an angle it passes through over time. Think of like revolutions per minute is an angular velocity. For our purposes and for the formulas that we're using, just like the other ones, we need to have our angles measured in radians. So that angular velocity, that theta over t, right, an angle over time, is always radians per unit time, and we denote it with, it looks like a W, but it's a lowercase omega Greek letter. V is the linear velocity, so that's like an arc length over time. And V and omega are related by this formula, V equals omega R. So this is sort of like the important formula here, and then this is sort of the new concept of angular velocity, an angle over unit time. So here's an example. We have a person on a hang glider moving along in a horizontal circular arc of radius 90 meters. They tell us the angular velocity is 0.125 radians per second. We want to find the linear velocity. So they've told us that R is equal to 90 meters. They've told us that omega is 0.125 radians per second. We want an angular velocity. So we start with our formula, V equals omega R, 0.125 radians per second times 90 meters. Now radians, as I mentioned before, are dimensionless. They will add nothing to the dimensions. And so the units we're going to end up with are meters per second. So 0.125 times 90 is 11.25 meters per second. Let's try another. In this example, they tell us a satellite maintains an altitude 22,320 miles above a fixed point on the equator. And if the radius of the Earth is 3,960 miles, what's the linear velocity of the satellite? Okay, so here's the Earth. It's got some radius. That's 3,960 miles. And then the satellite maintains a position above this fixed point. So as the Earth revolves, the satellite is always directly above that same point. And this is 22,320 miles. Now, they told us, we want to find the linear velocity, right? So, we're going to be using this. We need to know omega and we need to know R. The radius will be fairly simple in that the center of this big circle, this satellite is sort of moving along a big arc, right? And the center of that circle is the center of the Earth. So the radius is actually what we get when we add these two together. And it's 26,280. To find omega, what's really key here is that it's above a fixed point on the equator, just a fixed point. So its angular velocity is the same as the angular velocity of the Earth when it rotates on its axis. And so that is 1 revolution every 24 hours. And I want to just convert this into radians per hour. So 1 full revolution is 2 pi radians. We can reduce this. 2 goes into 24 12 times. We have pi over 12 radians per hour. And now we're ready to plug these in. Pi over 12 radians per hour times 26,280 miles. Radians are dimensionless. That means the units we're going to be left with are miles per hour. Six 1,880.09 miles per hour. All right, one more. A quick heads up. If they give you an angular velocity in radians per time, they'll actually write RAD over seconds or over minutes. Sometimes they're giving you an angular velocity in revolutions per unit time, and they abbreviate that with just a lowercase r. So it's important to note that when you're given an angular velocity as r per minute or r per hour or whatever, it's revolutions, not radians. In this example, we sort of see that at play here. They say that the flywheel of a steam engine is 0.30 meters in diameter. Okay, if it's revolving at 420 r per minute, so that's revolutions per minute. How fast is a point on the rim moving? So they tell us the diameter, so we're going to cut that in half to get the radius of 0.15. We need omega to be in radians per unit time. So let's start with the 420 revolutions. I'll just write REV over minute. And we want to get from revolutions to radians, so 1 revolution is 2 pi radians. And if we multiply that, we get 840 pi radians per minute. Now we're ready to use V equals omega r. So we have 840 pi radians per minute times 0.15 meters. Our units, when we do this, will be meters per minute because, once again, radians are dimensionless. So 840 pi times 0.15 is 395.84 meters per minute. We could leave it like this, or sometimes folks prefer meters per second. It's sort of a more common unit, so we could do that easy enough with a little dimensional analysis. 1 minute, 60 seconds. .597 or 6.60 meters per second. Okay, that finishes up chapter 2.